Hi folks, when you buy a 5-axis machine, one of the coolest parts is the ability to finish parts in one operation. Now if you've seen the trade shows or the YouTube videos, you see a lot of really fancy 5-axis simultaneous machining, but the reality is most 5-axis work is positional work. 3+2, orienting the part, the ability to work it from different angles, hold critical tolerances in one setup, and hopefully either finish the part in one operation or come really close to finishing it such that that second operation is a relatively minor amount of work. In this video, we're going to go through 8 different examples of 5-axis cam and fixturing workflows, part examples with an emphasis on tabbing the parts off or coming pretty close to getting the part done in one operation. So let's dive in. We're starting with a really basic workflow, and now we're cheating because this isn't tabbing, but that's a really important theme to 5-axis, which is don't use 5-axis if you don't have to. We've got this nice rectangular base part here, so there's no reason to get complicated with the workflow. In Op 1, we machine the bottom half of that part. So when that's done, we've got a nice square block of material that works for the work holding side for Op 2, and we've got good square surfaces that we can use for our X, Y, and Z work coordinate system operation for Op 2. And this particular part, there weren't quite as many tricky surfaces to blend or critical tolerances on this bottom half. So again, we finished that in Op 1. We can use our Renishaw probe to get a really good setup for Op 2. We've modeled some custom stock in Fusion 360 to represent what our Op 2 stock looks like. And then we can come through in Op 2 and really make use of the fact that we have a 3+2 machine or a 5-axis machine to work the part at various different angles. And that's one of the really cool things about 5-axis machining is we can do adaptive roughing around this full part, then we can come back and do certain contours at different angles, and then drilling and tapping at different angles, versus the need in a traditional setup where you really want to do all the work at that particular angle or orientation before you flip it into a different fixture. Next up, machining this V8 engine block. And we're generally working up from simplest to more complex as we go through these 8 examples. Here we're leaving a thick tab, meaning a tab that is strong enough to support the weight of the part. It's not going to tip over or deflect, which can cause problems with gouging the part or breaking the tool. I like to organize our cam file structure by using folders, with the last folder being this part off operation. If we hop back into the design space, we're driving that part off operation with 2 different 2D sketches. And the key to making this an elegant workflow is hopping back into the CAD environment. And our last sketch lets us define the thickness of that tab in one place and then spaced off the center line by that distance divided by 2, which keeps the tab centered. Anytime you've got a relatively long stick out combined with a relatively deep cut to the tool diameter, take a look at trying reduced neck or relieve neck tools. We used Helical part number 46246, which was a 3/8 inch reduced neck end mill. It's incredible how much more strength or how much stiffer the reduced neck is because you have a significant portion of the tool stick out as solid carbide versus having the flutes cut into it. You're still going to have to run it at relatively low feeds and speeds. We were running this at 200 surface feet and 1.5 thousandths of an inch feed per tooth, which is only 10 inches per minute. It's not the fastest way, but it tends to be a reliable way. You'll want to use radial stock to leave. That way you leave some additional material on that bottom surface. Once the part is done on the 5-axis machine, you can use a bandsaw to quickly zip off the remaining section of that material and then lay the part in a relatively inexpensive 3-axis machine and deck that final face for a machine finish and or to accurately set the part's overall height. Part number 3. This was a part we made for Project Egress, which was the partnership with Smithsonian to celebrate the 50th anniversary of Apollo. We had a bunch of parts to make in a relatively short period of time, so there was a huge emphasis on getting these parts cammed up quickly and made quickly. And now we're venturing into what we traditionally think of as tabs, which has morphed into this Instagram bragging rights competition on how little material can you hold apart when you do the flick. And while this is a good workflow to know, it's actually not always the best example of the way to fixture it. We'll talk about that a little more in the following few parts. But in this case, you've got a relatively heavy part and a relatively small tab. So one thing we know is going to happen is this part's going to tip over some. You've got to think about what sort of consequence that has. One of the things we're doing is putting this tab toward one side of the part. That way when it does tip over, which is going to tip away from the cutting tool and not tip into the cutting tool, which would cause it to pinch or bind that flute and certainly gouge the part, possibly damage the end. What we're left with is a really thin tab, and there's actually a trick in Fusion that we can use to measure that. We'll select those two operations that cut that final tab thickness. In simulation, under Info, we hover our mouse over a point on one of the toolpaths. We can see that it's approximately 4.11 inches. If we flip to the other one, we can see it's approximately 4.098 inches. And we're left with an approximately 15 thousandths of an inch tab. You can then cut that tab off with a pair of snips and finish blending it in with a Scotchbrite wheel, a hand piece of Scotchbrite, or a file, although it's generally tricky to get this to look really nice. But it works well if it's a non-critical face, or especially if it's a hidden feature. Let's improve the way we tab by, instead of having a single tab, having two or more tabs and having them on different planes, which is going to add a lot of stability to the part as it's tabbed off. And let's talk about this by looking at one of the first 5-axis parts that we ever made, and then looking at how we would do that now that we've had a few years to really learn and hone in our skills. So this is a part for our Johnny 5 robot build. We only had to make 2 of them, so it's a great candidate for a one-and-done workflow on a 5-axis machine. And it was also surprising to us how rigid of a setup this can be, even with a relatively thin piece of material hanging quite a ways out of the 5th-axis vise. So while we have the most rigidity in the part, we machine or rough out the material furthest away from our work holding. Then we rough out that large center bore. We work the part down, generally starting from the top to the bottom. We rely heavily on 2D contours to work around the part. We can control the toolpath on a 2D contour with this tangential extension. So on this part, we have well over half of this circle selected as the chain, and the toolpath would look exactly like that blue selection. But by doing a -4-inch tangential extension, we're taking that starting point and subtracting the first 4 inches of the toolpath. And this has some pros and cons as a CAM workflow. The pro is that it's very quick to do. The con is that it can be difficult to figure out what exactly that distance is, but it takes less time than the alternative, which is to hop back into the CAD workspace and create specific dimensioned sketch geometry. We're then left with a relatively thick tab, but we will machine one last relatively shallow slot along that back edge. That lets us come in with a chamfer tool while the part's still rigid, just to knock that edge off. We can finish up any other chamfers we need, and then we make use of a pretty cool feature in Fusion that allows us to automatically tab within 2D contour. Now again, this has some pros but some major drawbacks as well. The pro is again the speed. It's just so easy to hop in to the 2D contour, check that tabs box, choose the location and shape of your tabs. Here we've got rectangular tabs at a set width every 2 inches, and Fusion will automatically update this 2D contour toolpath to leave the tabs as specified. There are 2 major cons, and I'd love to see Autodesk fix these because I think they could really increase the functionality of this. The first is that the toolpath plunges. So as we're machining across this strip, as we start to form the tab, it's machining along, it lifts up to leave the tab, and then as it finishes across the tab, it plunges straight back down into the material. This is not a preferred machining strategy, and you'll generally hear your machine make a chirp or gripe when you do that. Switching the tabs to triangles can help by doing more of a ramped plunge, but in my opinion, it's still not a great solution. The other problem that I think could be easily solved is Fusion doesn't give us a way to then clean up these tabs later. I've created 2 different 2D contours that are located where those tabs are to zip them off from the other side, but I had to do that by plugging and chugging or guessing at the tangential extensions. It seems like it should be so easy for Fusion to give us remnant sketch geometry from where those tabs were to then come in on the flip side and zip them off. When you're doing this final toolpath, I like to leave some amount of radial stock. That allows the tool to cut the tab off, but it's not using the side of that end mill to try to machine the bottom of your part, because your part's no longer rigid enough to be a machine. So if you try to cut that off, it's just going to chatter or push that part away. All right, a year and a half later, let's show a much better way of doing that same part. Now it kind of looks the same. We still have two tabs along the bottom of our part, but there's two major differences. The first is that the way we got those tabs is completely different and so much better. The second is that those tabs are on different planes. We've got one toward the left edge of the part and the other toward the right edge of the part, which means as we thin those tabs out, the fact that they're not coplanar is going to offer a lot more tipping stability. So you're not going to get that good Instagram flick, but it'll be a much better workflow. The heavy lifting for this actually happens back in the CAD workspace. But the good news is that it's relatively easy, and it's a process that will cross over to a lot of different parts. What we want to do is create two different pieces of CAD geometry. The first is this relatively large block of material. We created a sketch on the bottom of our part. We can easily adjust the thickness at any point in time. And then a pro tip on how we extrude that, it's a pretty cool trick which you might not know if you're newer to Fusion. We do a normal extrude, we select that profile, but instead of doing the traditional distance, which would create a piece of geometry that remains angled relative to our fixture, we can change it to to object. We can select the jaw of our 5th axis vise. Now in this case, it's just construction geometry. We're not actually going to physically make this part. Nevertheless, it's a nice touch, and it's a feature or a trick that can really come in handy for this sort of a workflow. Back in the CAM workspace, the key is in our setup, we have two bodies. We have our part that we're actually making, and then we've expanded the CAD tree, and we've actually selected that larger tabbing body that we just made. What this means is that when we do an adaptive style toolpath, the adaptive toolpath is going to look at all the stock that it sees as defined in our model stock, but it's also going to look at anything in the setup that's defined as the model, and it's not going to machine the model. So it's a really easy way and a parametric way and a visual way of creating that initial large tab. If you haven't watched some of our other videos on 5th axis workflows, card here to a page on NYC CNC, but the major key here that prevents the toolpath from machining the rest of the stock that you see is that we're also using a sketch constraint. And this is something that's really commonly seen in both 3-axis and 5-axis workflows, where we have this green box selected as our machining boundary. And the toolpath is going to be anywhere it sees both an area within that green box, but then also within the stock selection. So it doesn't matter that we have some extra area in our green box up here because it's outside of the stock, but it's not going to cut down here, which is what prevents us from machining into our vise. So then back in the design space, we've got to create these tabs along two planes. To create those tabs on the two planes, we're going to leverage the existing geometry that we have from our larger tab. We're going to create two smaller tabs in the far left and the top right corner, like so. Extrude those down the same way so that they intersect with the jaw of our 5th axis vise. But now we have a problem, or a dilemma, I should say, which is we need to rough out the majority of this material from two different sides to leave those tabs before we start whittling those tabs down to a thinner state. They're pretty thick right now. We modeled them at 100 thou thick. Now, if you've watched our channel, you know that our go-to is 2D and 3D adaptive. We're certainly not unique in that. But here is a place where 2D and 3D Pocket really shine. And 2D Pocket works great for two reasons. The first is 2D Pocket is not adaptive. It's not going to try to create even equal cuts. And the reason that's great is it happens to give us a perfectly straight line along the bottom edge of our part. We're also taking relatively shallow cuts, kind of that old school machining style. We don't need that high-speed machining, trochoidal, really thin cutting. The other reason is it's just so easy. Under geometry, we have to make two changes. Just check rest machining. That's going to evaluate everything that's been machined up to this point, so we're not cutting air. And under model, we're going to uncheck the setup model, and instead we're going to pick our part, and we're going to pick the tabs on two planes. That's going to make 3D Pocket aware of those two tabs, and we'll run the first operation from the top side of the part and the second operation from the bottom side of the part. We're not plunging the end mill into the material to create the tab, and generally speaking, any updates we make to those tab locations or thicknesses in the CAD side, they're automatically going to flow into our CAM toolpath, which makes it so nice and convenient to just dial that perfect part in. The other benefit really pays dividends, which is that we now want to zip those tabs off or make them a lot thinner. We already have the CAD sketch data in our part, and again, it will remain parametric. We can zip this tab off from the top side. We not only have the tab's location, so we don't have to guess about our tangential extension, but we also have chosen the bottom of that tab, and we can simply use the axial stock to leave to drive the exact thickness of our tab. This is a lot easier than some of the other workflows where you're effectively guessing at how thick that tab is going to be. And the end result is awesome. We've got a part with a known tab thickness and known location with a fairly easy and straightforward CAD process that's also something that can be turned into a template approach to use on any part that comes across your desk. The downside is you still have to snip those tabs off and finish them either in a second operation or with a Scotchbrite wheel. So the next 4 parts, we're going to dive into those true one and done workflows. Method number 5, window machining. And window machining is probably my favorite 5-axis workflow for 3 reasons. Number 1, it lends itself very well to turning it into a fusion template with your whole machine, vise, stock fixture to drop a part in and get really good toolpaths. Second reason is that the inherent nature of window machining means you're leaving a window or strip of material all the way around the part, and this is something that you can adjust as needed for certain parts and gives you a lot more work holding stability and really solve some of those problems you saw from, say, the earlier part like that Johnny 5 bracket, where as soon as you start machining the part away, you're going to lose the ability to do critical, stable work toward the top of the part. And the final reason is that that window can serve as a self-fixturing method for a pseudo op2, which we'll come back to here in a second. We were running this part in a 5th-axis dovetail vise, and the dovetail vise has a major advantage over the self-centering vise, which is that it's a relatively small part. We want to maintain access to the part features with small tools and minimize stick out and gauge length. And the dovetail vise gives us much better access because it's a smaller part that sits atop a tapered pyramid. And we built this out as a template using stock parameters so that we can adjust not only the X, Y, and Z dimensions of our stocks, but even the taper angle and window thickness size. Card here to the NYC CNC page that recaps a couple of the Autodesk University 2019 videos, including Rob Lockwood's, where he walks through a phenomenal example of this workflow on a UMC 500. What this window container method lets you do is take your part, drop it in here, and adjust the window size, the thickness, the angles, the tapers as you see fit. It really is a great example of when you have the right tools built at your disposal, helps you make better parts and frankly just enjoy machining. The window machining method here allows us to leave a complete border around our part as we machine most of the critical features. We can then pick away at different areas of the part, at first leaving a tab at the top and the full strip on the bottom, then machine away the bottom, leaving 3 tabs, 1 at the top and then 1 at the bottom 2 corners. The tabs are inherently on different planes, so we've got that stability like we saw in the second Johnny 5 part where the part's not going to tip over, and it really just is a nice workflow. That's also a great segue though to the 6th technique, which is this exact same workflow all the way up to having the tabs in place. But before we machine away those tabs, we need to secure that part in place. And the easiest way we've found to do this is with, you ready for it? Hot glue. Hot glue works great because the hot glue gun itself is cheap. Heck, you might even own one. The hot glue itself is cheap. It's relatively low hassle. And by adding some hot glue to the areas that are already finished machining, you don't really want to machine through the hot glue because it tends to gum up the cutters or will really ruin any ability for chip evacuation. But we pop the part in place, and what that does is it gives enough stability so that when we pick away those final tabs, there's a pretty good chance you're going to come away with a one and done part with all faces machined and no witness marks on those final tabs. Number 7. Take a look at this part. If you need to, hit pause, stare at it, and see if you figure out what's going on here. Okay, welcome back. This part is courtesy of the Dr. Phil experience. Phil is a solid machinist who makes some absolutely beautiful parts and also has a really good class from Autodesk University on how he rapid prototypes 5-axis parts. What's awesome about this workflow is he's machining the clamp when he makes the part. So the coaster here is the part, but we've got the clamp tabbed. Now obviously we don't really care about the tabs on the clamp. We'll just snip those off. We can then take that clamp, move it over to these 4 holes, screw that clamp in place, which is going to hold our part to this fixture, and then hit cycle start again to machine that final operation. And last but not least, number 8, carbide slitting saws. Well, really any style slitting saw, but we've had a lot of good luck with carbide slitting saws, partly because they give exceptional surface finishes. Although it's a very different approach than 1 through 7, it definitely still counts as tabbing, because in this case, we had to make a relatively high number of these parts, and doing it in the 5-axis allowed us to avoid multiple setups. So after we did the traditional machining, we actually used the 5th-axis dovetail tool to come in and create and machine a backside chamfer. This part was critical to these parts coming off truly one and done. And we then came in with a carbide slitting saw, leaving just enough tab. We could break that part off and then dress it on a diamond stone, and it left an exceptional surface finish. And the trick that we found to using those carbide slitting saws is leveraging the CAD environment to create sketch geometry to drive that tool path. We projected the periphery of this part, we deleted this section right here, and then added in our lead in and lead out. And that was very deliberate, because what we want the saw to do, first off, plunge down such that it cleared the part profile, which is something that 2D Contour isn't traditionally going to do. It then moves out, which is key to leaving just the specific amount of tab, and then a straight lead out of the part. And the way we control that tab thickness is on our Slitting Saw 2D Contour, under the Passes tab, we're cutting with a radial stock to leave that's just slightly less than half the thickness of our part. As always, folks, hope you learned something, hope you enjoyed. Card here to the NYC CNC page where we've got links to everything we referenced in this video. Otherwise, folks, take care. See you soon.